So we've looked at Newton's first law. An object in motion remains in motion, an object at rest remains at rest unless acted upon by an outside force. We've also looked at Newton's second law. F is equal to ma. If you put a force on something, it creates an acceleration, and that's dependent upon how massive the object is. The bigger the mass, the lower the acceleration. We also looked at Newton's third law, that for every action, there's an equal and opposite reaction. These are Newton's three laws of motion. He does have one more law of gravity, but we'll get to that later. So today what I want to do is I want to start looking at some of these very specific forces. We've already talked about the normal force being the force that acts on, counteracts gravity, which lifts something up, right? It goes perpendicular to the surface. Today I want to focus on a different force. I want to focus on friction. Okay, so if you're not in the class today, we're going to be doing this lab, and I'm going to show you kind of how I got it set up. I've run all the data for you, so you've got a lot of data files to look at. Most of the data is marked very clearly at the top as to how I set things up, and then it gives you velocity graphs. So let me show you how this works. We're going to be looking at friction. We're going to be looking at an object moving across this wooden board. So we have two surfaces that are sliding next to each other. And what I have is I have a force probe. The force probe measures the amount of force that I'm pulling with. Okay? So I kind of made a little lasso around this brick because that's what I want to start pulling. So I got this brick, and I'm essentially going to be pulling it with this force probe. Now, I'm going to do my best to pull this at a constant rate. And if I pull it at a constant rate, that means this thing's in equilibrium. The force that I'm pulling with here is the same as the force of friction back there. So as long as I'm going at a constant rate, and I'm going to do my best here, we should have, this should be measuring the force of friction. So the variables that I'm going to change are three. I'm going to do three different experiments actually. The first one I'm going to change is I'm going to change the mass of the system. So instead of just, the first one I'll pull just the brick by itself. Then I'm going to pull the brick with a kilogram on it. So the second graph that you'll see, which will be force versus time, is going to be the brick with the weight on it. Then I'll do 2 weights, then I'll do 3 weights. So we're going to pull with different weights, changing the mass of the system, changing that pushing of the contact force together. So can you make a claim as to how changing the mass of the system actually affects the amount of friction? The second variable I'm going to change is I'm actually going to change the amount of surface area the two surfaces have to each other. So right now I've got the block on its back right here as I pull it across this. I'm then going to switch this so that I have the block on its side. Now I want to be very careful that I make this so that the duct tape that's covering this block is always the same surface in contact with the other. So I'm going to put the block on its side here as well, and I'm going to pull it. The third way I'm going to pull is I'm actually going to put the block up here like this on its toe, kind of high like this, and pull it. So this is a huge change in surface area. I went from the entire bottom of the brick to the side of the brick, which is about a third the surface area, to the toe of the brick, which is much less surface area from the back side. Can you make a prediction on what you think the changing in the surface area will do to the amount of friction? Then look at my data and see if you can make a claim to see if you have evidence to back up what you think is correct. The final variable I want to look at is actually the type of surface that it's moving on. So you'll see here I've got a piece of sandpaper that I have on my brick now. So how does pulling it with the sandpaper on the wood different than just pulling the brick on the wood? The third surface I'm going to do is I'm actually just going to take the brick by itself and pull it across the desk, because the desk is a much different surface than the wood. So does the type of surface, the two contact surfaces, make a difference in terms of friction? See if you can look at the data that I took and figure out if you can make a claim based on the evidence from that data. So I want you to look through the data and kind of see if you can't figure out what are the variables that have to do with friction. What are the ones that are important and what are the ones we don't need to pay attention to. Then you should have read through some of the things about friction and coming up with the equation for friction. You guys should be able to figure most of that out for yourself. I do want to talk about one thing that is a little bit confusing, and that's this idea of the coefficient of friction. So the coefficient of friction, we actually give the variable mu. We've kind of run out of letters in the alphabet, I guess, so we start borrowing some from Greek. And there are actually three different types of friction that we can talk about. The first type of friction is actually called static friction. And static friction means not moving. If things are not moving, we call it static friction. If you look at this football sitting on this desk, the frictional force between the football and the desk is called static friction. Now, what actually causes this? Friction is caused by the bumps in the surfaces of both the football and the desk. There's really no such thing as a perfectly smooth surface. Every surface kind of has these little bumps on it. You can think about my knuckles as kind of some bumps. And what happens is when you set another surface on top of that, those bumps kind of fit inside each other and actually kind of stick. It kind of like molds itself. I'm talking about microscopic little changes in the surface. This football, you can actually see some of the bumps on the football. They make this football bumpy because they want you to be able to grab it. The desk, of course, is not as bumpy, but if you took a magnifying glass or took the microscope and really got down there, you would see that there are bumps in the table. So when you set these two on top of each other, those things kind of mesh inside and they stick to each other. We call that static friction. And we would use the variable mu sub s in the equation. So it's actually the same equation for all the different types of friction. We just call it mu sub s. The other type of friction that's important is what's called kinetic friction. Kinetic means moving. So anytime you see the word kinetic, something's probably moving. So in this case, this would be if the football is sliding across the desk. The football is sliding across like this. So if the football is sliding, you can think about those little tiny microscopic bumps. And they are bouncing over one another, kind of like your fingers do if you go like this. They're not sticking together, they're bouncing over one another. For this reason, kinetic friction is almost always less than static friction. Static friction, there's enough force or enough mass, gravity, pushing down on this to make those microscopic things kind of stick together. But kinetic friction, they're just already moving and bouncing over one another. We actually see that a little bit in the lab. If you are pulling on this brick, it actually takes a little bit more to get it going, and then the brick starts to move fairly easily. I know I've experienced this a lot when I was a kid. So when I was a kid, I used to you'd want to rearrange your room, several times a year, I guess, when I was 10. So you want to move your dresser. And I was dumb. I never took the drawers out. I just got on the floor and put my back against the wall and tried to just kick the dresser. And if you've ever done this, you probably know how this works. You press, and then all of a sudden the thing gives. And you can think about it actually in the carpet. So the dresser actually makes these little indentations in the carpet, and then it's hard, but once you get them out of those indentations, the thing actually moves pretty easily. That's kind of the difference between static and kinetic friction. The third type of friction is actually called rolling friction, and that's something that looks like this. Do you suppose rolling friction is more like static or more like kinetic friction? Actually, rolling friction is more like static friction. Because if you think about it, those little bumps are not, sliding over one another. They're actually going down and then lifting up. They're pushing down and then they're lifting up. So they're pressing down and actually sticking for just a little bit. For this reason, rolling friction is actually probably better than sliding friction in terms of something, keeping something moving. A good example of this is what we call anti-lock brakes. In your car, we have these things called anti-lock brakes, where when you slam on the brakes, the tires don't actually, lock up. They continue to move. Because if they lock up, then the tire starts to slide and you're under static friction, which is typically less than, or I'm sorry, you're under kinetic friction as you're sliding, which is typically less friction than the rolling friction if your tires can continue to move. So in anti-lock brakes, they actually keep your tires moving so that you stay under rolling friction, and then you can actually stop quicker because there's more friction. The coefficient of friction is such a huge thing in engineering. Like, you wouldn't believe, there are people's jobs that all they do is they look at coefficients of friction and they try to make things better. Sounds kind of dumb, but they do an experiment very similar to yours. Think about if you work for Goodyear Tires. Do you suppose Goodyear Tires knows the coefficient of friction between their tires and asphalt? Yeah. There's engineers that spend a ton of time creating the type of rubber and the type of inserts into the rubber so that they can get the tires stickier to the asphalt. Do you suppose they know their tires on asphalt when it's raining? Or tires on different types of asphalt? Or tires after 10,000 miles or 100,000 miles on that asphalt? Sure they do. Do you suppose they look at different coefficients of friction with different treads in the tires and widths in the tires and all these different things? You're making the best tires you can. The idea for tires is that they stick to the road. Coefficient of friction is a huge part of their job. Do you suppose if you work for Nike, you know the coefficient of friction between the shoes and a basketball court? Do you suppose you know the coefficient of friction between the shoes and an unwaxed court or asphalt outside or all of these different things? They know exactly, because they want the shoes to stick to the floor, but not so much that you're going to turn an ankle. So there's a lot of play that goes into what are we going to make the bottom of that shoe out of? How are we going to keep that coefficient of friction exactly where we want it? I mean, coefficient of friction is everywhere. I think about my laptop here. My laptop has these little, rubber nubbies on the bottom here, right? That keep it from sliding. The person who engineered this laptop had to choose what kind of rubber they want right here. And then some other company probably manufactured this rubber in order to make it the exact coefficient of friction so that I can move my laptop around the desk, but it's still not going to slide off the desk and just onto the floor. So coefficient of friction is a huge part of engineering. There are jobs, like I said, good paying jobs, where a lot of what they do is focusing on coefficient of friction. Work through the worksheet. You're going to come up with the equation. The same equation works for all different types of friction. So it's not that big of a deal. Friction always works to stop motion, to slow things down. And really, you should be pretty good making it through this worksheet. So let me know if you have any questions, and I'll see you soon.